Hi, let's talk about how we've gotten away through these first 9 chapters with treating solid objects like particles. And the particle definition said we imagined that our object was occupying the tiniest possible space that we could imagine, where all properties of that object apply to that tiniest point. So if you do object-oriented programming, it's kind of like thinking that we're adding all of these just different parameters to our class of being our object, though we've just sort of pretended that the physical size, when it's needed for a calculation, is real, but otherwise it's practically zero. Well, we got away with that through being able to look at momentum and the behavior of a collection of particles when we average what's going on. So in our systems, we said we took a look at the total force acting on our system. Well, instead, we could break it out into individual atoms or individual tiny pieces of whatever system we have. And that would give us the sum of forces on object 1, the sum of forces on object 2, the sum of forces on object 3, through all of the n objects that make up our system. Well, the sum of the forces on our system is going to be the mass of our system, which is just the total mass times the acceleration of our system, which is what we could call the average acceleration. And similarly, applying that chapter 5 version of Newton's laws, we could say that the sum of the forces on object 1 is the mass of 1 times the acceleration of 1 plus the mass of 2 times the acceleration of 2, and so on. So that means then that our average acceleration, the acceleration of our system, would just be the sum over every element of the mass of that element times the acceleration of that element divided by the sum of all of those masses. And this is just a statistical process called taking a statistically weighted average of a value. So what we're averaging by here, our statistical weight, is the mass of our object. Now if I integrate both sides, I would get the velocity of my system. On the right-hand side, instead of looking at the accelerations, I'd be looking at the velocities. So the velocity of a system then is going to be the sum of the mass of each element times its velocity. That's just the total momentum. So the velocity of a system is just the total momentum of the system. The sum of the momentum of each part divided by the total mass of our system. So when we talk about the motion of solid objects, we're talking about sort of the average effect of the momentum of each individual piece that's making up our solid object. And to talk about the location of our system, well, I integrate both sides again, and that would give me the sum of each mass times the location of that mass divided by the sum of all of the masses. And if we were to just break this up coordinate by coordinate, that would allow us to calculate the location of the center of mass on the x-axis. It would be the mass of 1 times the x-coordinate of object 1, mass of 2, x-coordinate of object 2, mass of 3, x-coordinate of object 3. We're weighting the location of each object in our system by the mass, statistically weighting. We could weight by weight. We could take the mass of that object times the local strength of gravity times its location, add up all of those pieces, and then to account for that weight, we would then have to sum up the total number of weights that we had. The weight of object 1, mass 1 times the local strength of gravity plus mass 2 times the local strength of gravity, and so on. Now, if gravity is constant, like we've been assuming so far, then the center of mass is exactly the same as the center of gravity. But if the local strength of gravity can be changing, then the center of mass may not be where the center of gravity is. And the center of gravity is where the force of gravity is acting on an object. We find the individual sort of weight of each point divided by our total weight. That gives us where the force of gravity is acting on our object. Now, if we don't have a discrete countable number of points, say we have a uniform solid, well, what we could imagine doing is thinking of smaller and smaller and smaller possible elements until eventually we get an element that has an infinitesimal amount of mass. So my center of mass of that object would involve me summing up all of those little tiny elements of mass times their location. Well, summing up a whole bunch of infinitesimals is exactly what an integral is. So to find the x-coordinate of the center of mass over a distribution of mass, we would integrate x with respect to how our mass is spread throughout a system. And then we would sum up all of those little pieces of mass. Well, the integral of all of those little pieces of mass just gives me the total mass of my object. And for my y-coordinate, I'd integrate y with respect to all of those sums of all of those little pieces of mass, and then divide by my mass. And the same thing with z. The hard part of this is how we think about expressing a system in terms of mass. Well, usually, if we're working with coordinates, it's easier to think in terms of breaking up space into volume, and the density is going to be equal to the amount of mass we have divided by the amount of volume that we have. So that means then that an infinitesimal amount of mass would just be the density of our solid at that area times an infinitesimal patch of volume. So if we had something like a rectangular box, we could think about finding the x location. So if this marker is the rectangular box and it's laying along the x-axis, it has a cross-section, so a patch of volume would be a tiny amount of x times its cross-section. And if the cross-section changes, which it really does with this marker, if I could calculate an expression for that cross-section as a function of x, well then I just integrate that cross-section times x with respect to x and the density. Now the density could be constant, the density could be a function of x. And if the density is a function of x, then our integrals get a lot more complicated in a hurry. But if we're just dealing with a uniform solid would have a density that's just equal to the total mass divided by the total volume of our object. So if that's the case, then in terms of density, the x-coordinate of our center of mass would just be equal to the integral of x with respect to volume divided by the total volume of our object. The y-coordinate of our center of mass would be y integrated with respect to our volume divided by the total volume. So, as I said, the hard part is figuring out how to express the volume of an object as you move through that object in the direction that you're calculating the center of mass. And my recommendation is, if possible, look for symmetries in order to make your life as easy as possible. Thanks for watching.